There is a particular kind of darkness that belongs only to the desert at night. Not the soft, familiar dark of a city bedroom with its streetlight glow bleeding through the curtains. Not even the deeper dark of a countryside field, where your eyes adjust after a few minutes and the shapes of things come back to you slowly, reassuringly. No, the darkness of the desert at night is something else entirely. It is the darkness of a world that does not care whether you can see or not. It is vast and it is indifferent, and it stretches all the way from the ground beneath your feet to the stars overhead without interruption, without break, without the slightest acknowledgement that you are standing in the middle of it, breathing, wondering what it means. The ancient Egyptians understood this darkness better than almost any civilization that came before or after them. They lived beside it. They built their empire on the narrow green margin where the Nile met the desert, and every night, without exception, they watched the sun go down on one side of that margin and disappear into the rock and sand and absolute blackness of the world beyond. They watched it and they feared it, and they invented, across thousands of years of careful, anxious observation, an entire cosmology designed to explain what was happening in the dark while they slept. In the theology of ancient Egypt, the sun was not simply a star, it was Ra, the solar god, the bringer of light and order, the force that held the world together and kept the chaos at bay. Every morning Ra rose in the east and crossed the sky in a great celestial bark, a divine boat that carried the sun from one horizon to the other, while the world below went about its work, grew its crops, built its temples, lived its ordinary human life under the protection of that steady overhead light. And every evening, as the sun touched the western horizon and the light began to fail, Ra descended into something the Egyptians called the Duat, the underworld, the place beneath the earth where the dead went and where the darkness was not merely the absence of light, but an active, hostile force with its own agenda and its own name. Ra's journey through the Duat lasted 12 hours. 12 hours of navigating through absolute dark, through 12 chambers of the underworld, each one more treacherous than the last, carrying the sun on his bark toward the eastern horizon, where he would emerge again at dawn and the cycle would begin once more. It sounds simple enough, described that way. A god travelling through the dark, a sun rising in the morning. But for the ancient Egyptians, it was anything but simple, because somewhere in that darkness, waiting in every chamber of the underworld, was the one thing that Ra could never permanently defeat. The Egyptians called it Apep in their own language, though the Greeks who came later would give it the name by which we most commonly know it today, Apophis. It was usually depicted as a giant serpent, sometimes as a crocodile, but most often as a snake of impossible size, said to stretch 16 yards in length, with a head made of flint, hard and cold, and absolutely without mercy. It was not a god in the usual sense, because the Egyptians never built it temples, and no one ever prayed to it for favours or protection. It was something older than gods and more fundamental. It was the embodiment of chaos itself, the force of darkness and disorder that existed before creation, and that would outlast creation if it was ever allowed to win. It was the enemy of Ra, it was the enemy of everything. The Egyptians called it the enemy of Ra, and they called it the Lord of Chaos, and they called it the Serpent from the Nile, and all of those names meant the same thing. The force that, if left unwatched and unfought for even a single night, would swallow the sun and end the world. Every night, as Ra made his way through the Duat toward morning, Apophis attacked. The serpent would attempt to swallow the sun, to take the light out of the world permanently, and plunge everything into the void of nothingness from which creation had originally emerged. And every night, Ra and his allies fought the serpent back. Set, the god of storms in the desert, rode at the prow of Ra's bark and drove his great spear into Apophis's side. Isis and Neith and Serket used their magic to bind the serpent in nets. The justified dead, those souls who had made it through judgment and earned their place in the afterlife, fought alongside the gods as soldiers in an eternal war that never ended, and whose outcome was never finally decided. Even ordinary living Egyptians played a role, gathering in the great temples to burn wax effigies of the serpent, to spit on its image and mutilate it with blades, and recite the spells that would weaken it and strengthen Ra for the night's battle ahead. The collection of these spells was written down and preserved. The Egyptians called it the Book of Apophis, and it was read by the priests, and it was buried with the dead in case they encountered the serpent in the underworld and needed to know what to say. And every morning the sun rose. Ra had won again. The The serpent had been driven back into the darkness for another day, defeated but not destroyed, because Apophis could never be permanently destroyed. That was the terrifying thing about it, the thing that made it different from every other enemy in Egyptian mythology. You could kill Apophis tonight, and it would be back tomorrow, full of the same hatred and the same hunger, attacking Ras Bark with the same coiling strength as if last night's defeat had never happened. The battle never ended. It could never end. The only options were to fight it every single night or to stop fighting and lose the sun forever. Think about what it would mean to live inside that cosmology. To go to bed every night knowing that the sun's return tomorrow morning was not guaranteed, that it depended on an ongoing battle being won in the darkness below the earth while you slept. Think about watching a solar eclipse, a midday sky going dark with no warning, and believing with your whole heart that it meant Apophis was winning, that the serpent had gotten its coils around the sun and was in the process of swallowing it. The ancient Egyptians believed exactly that. Solar eclipses were moments of particular terror, brief windows of genuine existential dread, because they looked like proof that chaos was stronger than order on that particular day, and that the outcome was not yet decided. They were wrong about the mechanism, of course. They did not know about orbital mechanics, about the moon passing between the Earth and the Sun, about the geometry of shadows in space. But they were not wrong about the feeling. That feeling of watching the light go out in the middle of the day and not being certain it will come back is one of the most ancient human experiences there is, and it was real long before anyone knew what caused it. There is something almost unbearably human about all of this. The need to look at a dangerous and indifferent universe and give it a shape, a name, a narrative. The need to feel that the darkness is not simply absence but presence, not simply random but purposeful, so that it can be opposed, fought, named, and eventually understood. The Egyptians named their darkness Apophis and gave it the form of a serpent because a serpent can be fought. A serpent can be pinned with a spear and bound in nets and driven back into its hole. A void cannot. A void just is. And so the priest burned their wax figures and recited their spells and went to sleep believing, really believing, that their efforts were part of the battle, that human vigilance and human ritual were genuine contributions to the war against the dark. They were not entirely wrong about that, as it turns out. The human instinct to watch the night sky, to track the movements of things overhead, to build instruments capable of seeing what the naked eye cannot, to calculate and predict and prepare, that instinct is a direct descendant of the Egyptian priests standing in their temples in the small hours of the morning, staring up at the stars, refusing to stop paying attention to what was moving through the darkness above them. We gave up the serpent and the bark and the wax figures a long time ago, but we kept the watching. We kept the careful, patient, systematic observation of what moves through the dark. And in the summer of 2004, that watching revealed something that no astronomer had ever seen before. Something that gave the old myth a suddenly very literal edge. Something that made the name Apophis feel less like ancient poetry and more like a warning. In June of that year, at the Kitt Peak National Observatory in Arizona, 3 astronomers found a new object moving through the inner solar system. Its name at that point was a string of numbers and letters that meant nothing to anyone outside a narrow scientific community. It moved the way near-Earth asteroids move, in a long elliptical orbit that swept it close to the Sun and therefore close to us on a regular schedule. Standard procedure, routine science, the kind of observation that happens thousands of times a year at survey telescopes around the world and almost always produces nothing more interesting than a new entry in a catalogue. But when they ran the numbers forward, when they calculated where this particular rock was going with increasing precision over the months that followed, what came back from the calculations was something that sent a quiet chill through the planetary science community and eventually through every newsroom on Earth. The rock was heading toward Earth, and the date was April 13th, 2029. The probability of impact was 2.7%. No asteroid in the history of modern astronomy had ever registered that high on the Torino scale, the international system used to rate the threat level of near-Earth objects on a scale from 0 to 10. This rock hit level 4, the highest any asteroid had ever reached. Level 4 means a close encounter that merits careful monitoring, that carries a probability of regional destruction greater than 1%, that is significant enough to warrant informing the public. And when it came time to give this rock a permanent name, when the asteroid received its formal designation as 999942, and its discoverers reached for the mythology, as the convention requires, there was really only one name that fit. They called it Apophis, the Lord of Chaos, the serpent that attacks in the dark and can never quite be destroyed. It was a more accurate name than any of them knew at the time. Tonight, we are going to find out exactly how accurate. The story of how we found Apophis is itself a story about the way science works at its best, which is to say slowly, carefully, and with a great deal of revision along the way. It is a story about instruments pointed at the sky in the middle of the night, about numbers that did not add up the way anyone expected, about a community of researchers who looked at those numbers and decided, against every instinct that says bad things do not happen to organized modern civilizations, that they needed to take this seriously. The three people who first spotted Apophis were Roy Tucker, David Tholen, and Fabrizio Bernardi. They were working at Kitt Peak National Observatory in southern Arizona, a cluster of white domes sitting on top of a mountain in the Sonoran Desert, one of the best places in North America to look at the sky because of its altitude and its distance from city lights and its reliably clear nights. Tholen in particular had spent years hunting near-Earth objects, small rocky bodies whose orbits bring them into the inner solar system and therefore into occasional proximity with our planet. It is painstaking work. You point a telescope at a patch of sky, you take an image, you wait, you take another image of the same patch of sky a little while later, and then you compare the two images. Most things in the sky do not move between one image and the next. Stars are so far away that even over weeks and months they appear stationary, fixed in their constellations as they have been since before any human civilization gave them names. But asteroids are close. They are in the neighbourhood, orbiting the Sun as we do, and their proximity means that even over the course of a single night they move visibly against the background of fixed stars. You look for the things that move, that is the whole job. On June 19, 2004, they found something moving. It was faint, close to the limit of what their instruments could detect, and it was moving in a way that was consistent with a near-Earth asteroid on a routine orbit that would bring it somewhat close to our planet sometime in the relatively near future. They logged it. They gave it the provisional designation 2004 MN4. They passed the observations onto the Minor Planet Center, the international clearinghouse for this kind of data, where the numbers would be combined with any other observations anyone else might have taken of the same object, and the orbit would be calculated and refined as more data came in. In the months that followed, the orbit of 2004 MN4 was refined by additional observations from observatories around the world, and as the orbit became more precise, a problem emerged. The range of possible trajectories for the asteroid, the envelope of paths it might be taking depending on exactly where it was and how fast it was moving, within the limits of observational uncertainty, kept including Earth. Not skirting Earth's neighbourhood in a vaguely concerning way, actually including Earth. The zone of uncertainty around the predicted path of this rock overlapped with the volume of space our planet would be occupying in April 2029, and no matter how astronomers tried to refine the numbers, they could not make that overlap go away. In December of 2004, the calculations reached a point where the probability of impact on April 13, 2029 was formally estimated at 2.7%. This number requires a moment of careful interpretation, because 2.7% sounds small. It is small. It means that out of every 100 possible realities branching from that moment, 97 of them involve the asteroid missing Earth entirely and continuing on its orbit without incident. But the remaining 3 involve it hitting us, and those 3 possibilities represent a level of genuine risk that the planetary science community had never faced before with a specific, named, real object on a real calendar date. The Torino Impact Hazard Scale had existed since 1999 as a way of communicating the level of concern associated with any particular near-Earth object, using ratings from 0, meaning no danger, to 10, meaning certain collision and global catastrophe. The scale was mostly theoretical. No asteroid had ever gotten above level 1, and most registered at level 0, which means effectively 0 chance of impact. 2004, MN4 hit level 4 in late December 2004 and briefly touched the discussion of level 5 as the probability estimates continued to be revised upward before better observations began pulling them back down. Level 4 had never been reached before. It has never been reached again since. The media noticed. There was a period of several weeks in late 2004 and early 2005 when headlines about the asteroid that might hit Earth in 2029 competed with coverage of the 2004 Indian Ocean tsunami, which had killed more than 200,000 people on December the 26th, and which dominated the news cycle for weeks. The timing was strange and terrible. One catastrophe was happening in real time on the other side of the world, killing hundreds of thousands of people with no warning. The other catastrophe was not yet certain, and was 25 years away, but it was being seriously discussed by serious scientists with peer-reviewed calculations behind it. For a moment in early 2005, the world had both things in its head simultaneously: the ocean that had just killed 250,000 people, and the rock that might kill millions more 2.5 decades hence. Then better observations came in, and the probability started to fall. As additional data refined the orbit of 2004 MN4, the range of uncertainty around its trajectory gradually shrank. More and more of the possible paths through that uncertainty corridor missed Earth. The probability fell from 2.7% to 1.6%, then to less than 1%, then to fractions of a percent. The Torino scale rating was dropped to level 1 in August 2005, then to level 0 later that year. There was a brief resurgence of concern in 2006 when astronomers calculated that even if the asteroid missed Earth in 2029, it might pass through what they called a gravitational keyhole, a specific region of space where Earth's gravity would be strong enough to pull the asteroid's orbit into a path that would bring it back for another encounter in 2036, this time potentially on a collision course. But further observations ruled out the 2036 impact as well, and the probability of any impact before 2100 was progressively reduced to less than 1 in a million, and then came March of 2021. By then, the asteroid had received its permanent name, Apophis, and its permanent designation 99942, and it had been watched by telescopes around the world for nearly 17 years. In early March 2021, Apophis made a relatively close pass of Earth, not as close as the 2029 approach would be, but close enough that the most powerful radar telescopes on the planet, including the Goldstone Solar System radar in California's Mojave Desert and the Green Bank Telescope in West Virginia, could get a precise fix on its position and velocity. The radar observations reduced the uncertainty in Apophis's predicted position during the 2029 encounter from hundreds of kilometers to just a few kilometers, and with that level of precision, the conclusion was unambiguous. Apophis would not hit Earth in 2029. It would not hit Earth in 2036. It would not hit Earth in 2068. NASA and the European Space Agency jointly announced on March 26, 2021, that Apophis had been removed from all impact risk lists. The serpent had been defeated. Not burned in wax, not bound in nets, but measured with radar and mathematics and 17 years of patient systematic observation until its orbit was known with certainty good enough to call it safe. But the precision of that certainty revealed something else entirely, something that, depending on your disposition, might be even more remarkable than the discovery that Apophis was going to hit us had been. Because when astronomers plotted the confirmed highly precise orbit of Apophis through the spring of 2029, what they found was that the rock was going to come genuinely, extraordinarily, almost incomprehensibly close to Earth without hitting it. To understand how close, you need a frame of reference. The Moon is on average about 384,000 kilometers from Earth. That is the distance that shapes our sense of what close means in the solar system, because the Moon is the most prominent object in our night sky, and its distance is woven into the way we intuitively understand cosmic scale. When people say an asteroid passed close to Earth, they sometimes mean it came within a few lunar distances, a few 100,000 kilometers, concerning, worth noting, but safely within the zone of near misses that planets experience on a regular basis over geological time. Apophis in April 2029 will pass approximately 32,000 kilometers from Earth's surface, not 32,000 kilometers from the center of the planet, from the surface. That is less than 1/10 the distance to the Moon. To put it in terms of artificial infrastructure rather than natural satellites, geostationary satellites, the communications and weather and navigation satellites that orbit at an altitude of roughly 36,000 kilometers, and that are responsible for a significant portion of global telecommunications, will be farther from Earth than Apophis will be at the moment of closest approach. The asteroid will pass beneath the ring of geostationary satellites. It will be, in the most literal sense possible, closer to Earth than the satellites we have put up there ourselves. No asteroid of Apophis's size has ever been observed passing this close to Earth in all of recorded history. No asteroid this large has approached this close since long before any human being existed to look up and notice. The best estimates suggest that an asteroid of this size passing at this distance is an event that occurs, on average, somewhere around once every 7,500 years. The last time it happened, there was no telescope to track it, no computer to calculate its orbit, no scientific tradition sophisticated enough to register the significance of what was moving through the sky above whatever civilization was trying to make sense of the world at that moment. We are the first civilization to see this coming. We are the first civilization with the instruments to find it, the mathematics to calculate its path, and the knowledge to understand what we are looking at. That is worth sitting with for a moment before we go any further. The rock has been out there for the entire 4.5 billion year history of the solar system. It has made countless close approaches to Earth over that time, or at least approaches that fell within the vicinity of Earth's orbit, each one unobserved, uncatalogued, unnamed. In 2004, for the first time, the right people were pointing the right instruments at the right patch of sky at the right moment, and the rock acquired a name and a number and a trajectory and a place in the global conversation about what we need to worry about. And what we found when we named it and tracked it and calculated its path with steadily increasing precision was this: it is going to miss us, but just barely. And before we let the relief of that near miss wash over us completely, before we close the file on Apophis and move on to other concerns, we should spend some time with a different question. A question that the planetary scientists themselves have spent time with, that has been the subject of papers in peer-reviewed journals and presentations at scientific conferences and simulations run on some of the most powerful computers available to the research community. What would happen if it did not miss? Not the philosophical question of what we would feel about it, or the geopolitical question of how governments would respond in the years before impact, or the cultural question of what art and religion and ordinary human life would look like in the shadow of a countdown. Those are fascinating questions, but they are not the ones we're going to sit with tonight. Tonight we are asking a more specific and more uncomfortable question, the question that sits underneath all the others and gives them their weight. If Apophis, this 370-metre rock shaped like a peanut, this boulder approximately the height of the Empire State Building and roughly 3 times as wide and long, if this specific object travelling at roughly 7.4 kilometres per second relative to Earth were to meet our planet rather than pass it by, what would the physics of that meeting produce? What would the atmosphere do? What would the ground do or the ocean do? What would happen in the minutes and hours and days and years afterward? How much of the world would be affected and in what ways and for how long? These questions have been studied. The answers are known, at least approximately, and they are, it must be said, remarkable, in the way that all extreme physical events are remarkable, in the way that forces operating at scales far beyond ordinary human experience are always remarkable, which is to say, they are both more and less catastrophic than you probably expect. Let us start at the beginning. Let us watch the serpent come. Before we go into the hypothetical, before we let the serpent do what the serpent is actually coming to do in the story we are about to tell, it is worth spending some time with what is actually going to happen in April 2029, the real event, the one the telescopes are tracking and the spacecraft are preparing for, and the 2 billion people in Europe and Africa and Western Asia will be able to watch with their own eyes without any equipment at all. Because the real event, the confirmed, predicted, mathematically certain event, is remarkable enough on its own terms to deserve a moment of genuine appreciation before we slide into the alternative history that is the point of tonight's journey. The date is April 13th, 2029, a Friday. Friday the 13th, specifically, which is either a remarkable coincidence or the universe's way of making sure that the superstitious among us have something to point to later. On that evening, depending on where you're standing on Earth, you will either be inside or outside the zone of visibility for the passage of Apophis, and if you are inside that zone, in the right part of Europe or Africa or Western Asia, and if you know where to look, and if you go outside and let your eyes adjust to whatever darkness is available, you will be able to see Apophis with your naked eye. not as a dramatic fireball, not as a streak across the sky, as a point of light, a little brighter than the faintest stars visible on a clear night, moving at a speed that will be perceptible if you watch for a minute or two, covering a distance in the sky equivalent to the apparent width of the full moon every 60 seconds. It will look like a star that has decided to go somewhere. 2 billion people will have the opportunity to see this. That figure, offered by the MIT planetary scientist Richard Binzel, who has spent much of his career studying near-Earth objects, puts the scale of the event in human terms that the astronomical numbers alone cannot quite convey. 2 billion people. The Apollo moon landings, arguably the most watched live events in the history of television up to that point, were seen in real time by roughly 500 million people. The passage of Apophis, visible to the naked eye, free of charge, requiring no equipment and no subscription, and no notification from a government agency, will be available to 4 times that number. 4 times the audience of the moon landings, watching a rock the size of a small mountain slide past our planet at a distance that is, by the standards of cosmic geography, essentially zero. The scientific community has prepared for this event with an intensity that reflects both its scientific value and its planetary defense implications. 3 spacecraft from 3 different space agencies will be in the vicinity of Apophis as it makes its close approach. NASA's OSIRIS-APEX, which was previously the OSIRIS-REx spacecraft that successfully returned samples from the asteroid Bennu to Earth in September of 2023, has been redirected on a course to intercept Apophis. It will arrive just after the asteroid's closest approach to Earth and spend the following 18 months studying the rock in extraordinary detail, mapping its surface down to features just a few centimeters across, measuring its internal structure, and eventually firing its thrusters to stir up the surface material and expose what lies beneath, so that scientists can analyze the composition of an asteroid in a way that has never been done before at this level of resolution. The European Space Agency is sending Ramses, the Rapid Apophis mission for space safety, which is scheduled to launch in the spring of 2028 and catch up with Apophis before its closest approach to Earth, giving scientists a before and after comparison of what the asteroid looks like before Earth's gravity has had a chance to affect it and what it looks like afterward. Japan's JAXA is contributing Destiny Plus, a spacecraft that will add additional observational capacity to what is already the most intensively planned asteroid encounter in the history of planetary science. Why all this preparation if we know Apophis is going to miss us? The answer is that the close approach itself is a scientific event of enormous value. When Apophis passes within 32,000 kilometers of Earth, our planet's gravity will exert a significant tidal force on the asteroid's surface. Research published in 2024 by scientists at the Johns Hopkins University Applied Physics Laboratory predicted that this tidal interaction will likely trigger tremors across the asteroid's surface, beginning approximately 1 hour before closest approach and continuing for some time afterward. The asteroid's gravity is about 250,000 times weaker than Earth's, which means that forces that would be trivial on our planet, forces comparable to gentle earthquakes, could be enough to loft boulders off Apophis's surface and send landslides cascading down its slopes. The close approach may also gradually change the asteroid's rotation rate over time, a slower effect that will play out over thousands of years but will be initiated by the 2029 encounter. All of this is happening to a rock that is, it bears repeating, safe. That will pass us by and continue on its orbit. That poses no danger to Earth in 2029, or in 2036, or in 2068, or in the next 100 years of calculated orbital mechanics. But here is where we make our turn. Here is where we step carefully through the door that the hypothetical opens. Because the margin between the predicted miss and a strike, while large enough in absolute terms to be certain, was not always certain, and before it was certain it was not always large, and the scientific literature contains detailed, peer-reviewed, fully calculated models of what would happen if the asteroid were to have followed a slightly different path through the gravitational dynamics of the inner solar system in the years and decades before 2029. Those models exist because the scientific community takes this work seriously, because understanding what an impact would do is not merely an academic exercise, but part of the foundation of planetary defense, because you cannot prepare for something you have not attempted to understand. Those models are what we're going to explore tonight. The hypothetical begins here. Apophis is approaching Earth on a trajectory that, in this version of events, carries it not past our planet but into it. Everything else in the scenario is the same. The asteroid is the same size, the same shape, the same composition, moving at the same velocity. The only thing that is different is a single variable in the orbital mechanics that sent it on a path to impact, rather than a path to close approach, a tiny difference accumulated over years of gravitational interactions with the Sun and the planets, invisible until it was too late to do anything about it. The serpent is coming, and this time, Raz Bark is in the way. Before we let the rock arrive, before we walk through what the physics and the geology and the oceanography and the climatology tell us about what an Apophis impact would produce, we need to establish something clearly and with some care. The scientists who have modelled this impact did not do so out of morbid curiosity or a taste for disaster fiction. They did it because understanding the consequences of an impact is foundational to the work of preventing one. You cannot design a deflection strategy for an asteroid without understanding what the asteroid would do if deflection failed. You cannot prioritise targets for planetary defence funding without being able to compare the potential damage from different sized impactors striking different types of terrain. The models we are about to draw from are serious scientific work, published in peer-reviewed journals, conducted by researchers at places like the Johns Hopkins University Applied Physics Laboratory, Purdue University, the USGS, and dozens of other institutions whose job is to take these questions seriously and answer them as rigorously as the available data allows. What those models tell us about Apophis is this: it would be catastrophic and it would be survivable. Those two things are both true simultaneously, and holding both of them in your head at the same time is necessary for understanding what we are actually talking about when we talk about an Apophis-class impact. The catastrophic part first. Apophis measures approximately 340 to 370 metres across at its widest point, with a longer dimension of roughly 450 metres and a shorter dimension of about 170 metres. It is described as peanut-shaped, or possibly egg-shaped, which is not the shape that most people picture when they think of an asteroid, but which is actually quite common for objects of this size in the solar system because many of them are contact binaries. Two smaller rocks that drifted together and stuck, and so they look like two spheres that have been squashed against each other until they form one elongated irregular shape. If you took Apophis and set it down in Central Park in New York City, it would not fit. If you set it down in a larger open space, say the Battery at the southern tip of Manhattan, it would fill that space completely and its top surface would sit roughly at the height of the Empire State Building. That is the physical scale of the thing, not continent-sized, not mountain range-sized, but also not negligibly small. Apophis travels at approximately 7.4 kilometers per second relative to Earth at the time of encounter. This is a number that deserves some translation into human terms. A kilometer per second is roughly 2,237 miles per hour. A bullet from a high-powered rifle travels at roughly 1 kilometer per second. The fastest aircraft ever built, the SR-71 Blackbird reconnaissance aircraft, could reach speeds of approximately 1 kilometer per second under ideal conditions. Apophis is moving 7 times faster than the fastest aircraft ever built, and it has been doing so for the entire 4.5 billion years of its existence. When it enters Earth's atmosphere, the air cannot get out of the way fast enough to simply flow around the asteroid the way it flows around a passenger jet. Instead, the air directly in front of the asteroid is compressed so rapidly that it heats to temperatures comparable to the surface of the Sun. The asteroid is flying through a sheath of plasma. It is generating its own light, its own heat, its own electromagnetic effects, simply by moving through the thin gas of our atmosphere faster than the gas can respond. The energy released by the impact would be approximately 1,200 megatons of TNT. This number appears in multiple independent estimates from multiple research groups using different methodologies, and so it can be treated with reasonable confidence. To understand what 1,200 megatons means, it helps to work backward through a series of comparisons. The atomic bomb dropped on Hiroshima in 1945 had a yield of approximately 0.015 megatons of TNT. 1,200 megatons is therefore roughly 80,000 times the energy of the Hiroshima bomb. The United States and Russia together possess nuclear arsenals with a combined yield estimated at somewhere around 1,460 megatons. The impact of Apophis would release energy roughly comparable to the simultaneous detonation of the entire combined global nuclear arsenal. Every nuclear weapon that has ever been built by every country that has ever built them detonated all at once in a single point. That is the energy released by one 370-meter rock falling from space. For more immediate comparison, the Tunguska event of June 1908, when an asteroid or comet fragment estimated at somewhere between 50 and 80 meters across exploded in the atmosphere above Siberia, released approximately 10 to 15 megatons of energy, and flattened roughly 2,000 square kilometers of forest, approximately 80 million trees brought down by the shockwave of a rock that never even reached the ground. Apophis is 4 to 7 times larger than the Tunguska object in diameter, and because energy scales with the cube of the impactor's size and velocity, it carries somewhere between 80 and 200 times more energy. The Tunguska event would have destroyed any city it occurred above. An Apophis impact would destroy everything within hundreds of kilometers of the impact point and cause measurable effects across a much larger region. And yet, the asteroid that killed the dinosaurs, the Chicxulub impactor that struck the shallow seas of what is now the Yucatan Peninsula 66 million years ago, and triggered the mass extinction that ended the Cretaceous period and the reign of the non-avian dinosaurs, that impactor was approximately 10 to 15 kilometers wide. It released an estimated 100 million megatons of energy, roughly 80,000 times more energy than Apophis would release. It vaporized billions of tons of rock and sulfur and seawater. It launched enough debris into the stratosphere to circle the entire globe within hours. It caused a years-long impact winter that dropped global temperatures by nearly 30 degrees Celsius and killed 3/4 of all species on Earth. Apophis, at 200 megatons against Chicxulub's 100 million megatons, is roughly 80,000 times less energetic. It would not cause a global mass extinction. It would not end human civilization. It would not trigger an impact winter that threatened the global food supply. What it would do is kill a very large number of people and devastate a region whose size depends critically on where it hits. And that is where the story branches, because the Earth is mostly ocean, specifically about 71% ocean, and an impactor striking anywhere on the planet has a roughly 7 in 10 chance of hitting water rather than land. And the consequences of those two scenarios are dramatically different in ways that we need to understand carefully. The story of an Apophis impact is not one story. It is 3 stories, and which one comes true depends on where the serpent falls. The first story is the land strike. The second is the ocean strike. The third is the airburst. Let us take them one at a time, and let us be as specific as the science allows. The first story begins somewhere over Central Europe, or the Middle East, or the interior of a continent, though the specific geography matters less than the physics, and it is the physics we need to understand. Imagine the asteroid entering the atmosphere not as a quiet event, but as a sudden transformation of the sky. For the people on the ground beneath it, there is no advance warning of any practical value. The light arrives first. An intensely bright streak appears in the sky, brighter than the sun if you are close enough to be in danger, bright enough to cast sharp shadows in the middle of the day, or to light up a nighttime landscape as though a second sun had briefly been installed at low altitude. This light is the compressed, superheated plasma that forms around the asteroid as it meets the atmosphere. The asteroid itself is invisible inside the fireball it is generating. What you see is the light of millions of tons of air being compressed so rapidly that it glows. Then comes the sound, or rather first comes the silence, the brief uncanny silence that follows the flash, because sound moves so much more slowly than light, and the interval between them is long enough, at great distances, to feel almost peaceful. And then the sound arrives, and there is nothing peaceful about it. The pressure wave generated by a 370-meter impactor, moving at 7.4 kilometers per second, is not a noise in any ordinary sense of the word. It is a physical force carried by the air, a sudden compression of the atmosphere so intense that it is capable of destroying structures, shattering windows across vast distances, rupturing eardrums, throwing people off their feet and stripping the surface off of buildings before the heat or the ejector or any other effect of the impact has had time to reach. The asteroid reaches the ground in approximately 12 seconds after entering the upper atmosphere. 12 seconds from the first visible flash to impact. The rock is too large to be meaningfully slowed by the air. Smaller asteroids, objects in the range of tens of meters across, lose most of their velocity in the atmosphere and can even disintegrate entirely before reaching the ground, releasing their energy in an airburst high above the surface. That is what happened at Tunguska in 1908 and at Chelyabinsk in 2013. Apophis is different. Apophis punches through the atmosphere with only minimal deceleration, arriving at the ground with the vast majority of its original kinetic energy intact. The moment of contact with the ground is described in the scientific literature with a precision that is almost clinical, which is perhaps the only way to describe something for which ordinary language is genuinely inadequate. The asteroid strikes the surface and the kinetic energy is converted in a fraction of a second into heat and pressure and motion. A crater forms. Research published in the scientific literature calculates that an Apophis-sized impactor striking sedimentary rock would excavate a crater approximately 5.1 kilometers across. 5 kilometers of rock, compressed, heated, and thrown outward in every direction in an explosion that operates on timescales so fast that the material does not have time to behave like rock. It behaves like a fluid. It flows outward in a great circular wave, the crater forming from the center and expanding outward while a curtain of ejected material, superhot fragments of rock that have been vaporized and then recondensed, rises into the stratosphere. The immediate blast radius, the zone where the overpressure from the explosion is sufficient to destroy virtually all structures and kill virtually all unsheltered people, extends for dozens of kilometers in every direction from the impact point. Beyond that, out to perhaps 100 or 200 kilometers depending on local terrain, the effects are still catastrophic but survivable for people who have some form of shelter. Windows shatter, buildings lose their walls, trees are stripped of their leaves and branches and in many cases snapped off at the base, as they were at Tunguska, by an invisible force that moves through the air faster than any storm. The ground shakes. Not the gentle rolling shaking of an ordinary earthquake, but the sharp, violent shaking of a seismic event equivalent to a moderate magnitude earthquake, generated by the impact energy coupling into the ground and propagating outward as seismic waves. The fires come next. Not in the immediate impact zone where the heat is so extreme that there is nothing left to burn, but in the intermediate zone where the thermal radiation from the expanding fireball is intense enough to ignite anything flammable: wood, cloth, grass, the surfaces of buildings, the clothing on people's backs. Fires start across thousands of square kilometers simultaneously. In the days and weeks that follow, depending on weather conditions, these fires merge and spread, consuming landscapes that the blast wave has already damaged and dried. The ejector that went into the stratosphere comes back down. Fine particles of pulverized rock and vaporized material settle slowly over hours and days, falling across a region much larger than the immediate impact zone, coating surfaces with a thin layer of grey dust and reducing the amount of sunlight reaching the ground below the dispersing cloud. This is not the global impact winter that the Chicxulub impactor caused, not even close. The Chicxulub impact put so much material into the stratosphere that it blocked sunlight on a global scale for years. An Apophis impact would put far less material into the stratosphere, enough to affect regional temperatures slightly over weeks to months, but not enough to threaten global agriculture or trigger a multi-year climate disruption. Using the computer simulation tool NeoSim, researchers estimated that a hypothetical impact of Apophis in a densely populated area like portions of Colombia and Venezuela, which lay along the previously calculated path of risk for the then-feared 2036 impact scenario, could produce more than 10 million casualties. 10 million people. The number sits on the page and it is very hard to process. The deadliest single day in modern history was September 1st, 1939, or perhaps December 7th, 1941, or perhaps September 11th, 2001, depending on what events you're counting and what scale you're using, but none of those events killed 10 million people. The deadliest natural disaster in recorded history, the 1931 China floods, may have killed somewhere between 1 and 4 million people. An Apophis land strike on a densely populated region would dwarf any natural disaster in human history in terms of immediate casualties, but the full picture requires geography. Most of Earth's land surface is not densely populated. A strike in the middle of the Sahara Desert, the Australian outback, the Canadian Shield, the Amazon Basin, Central Siberia, the depths of Antarctica, would be a geological event of extraordinary violence, but a human catastrophe of relatively modest scale. The casualties might number in the thousands rather than the millions, depending on how close the nearest population centres were and what the wind patterns carried in the following days. This is not reassurance exactly, because a one in several chance of a densely populated strike would still make an Apophis impact one of the worst disasters in human history across every possible scenario. But it is context. The planet is not uniformly occupied, and the specific consequences of an impact depend heavily on where the serpent falls. Now the second story, the story of the ocean strike. And this is where things become, in certain respects, more complicated, because an ocean impact would be simultaneously less immediately devastating in its ground zero effects and potentially more globally distributed in its consequences, depending on the geometry of where the rock hits and which coastlines lie in the path of what comes next. When Apophis strikes the ocean, the physics are different from the land strike in one critical way. There is no permanent crater. A 370-metre impactor striking the deep ocean would excavate a cavity in the water and in the seafloor beneath it, a cavity that researchers at the Planetary Society calculated would be approximately 7 kilometres wide. 7 kilometres of ocean floor exposed momentarily to the atmosphere as the water was thrown outward by the impact, before the surrounding ocean rushed back in and filled the void with a roar that would generate sound waves detectable by seismographs around the world. But the water that was thrown outward does not simply dissipate. It becomes waves. The waves generated by an Apophis ocean impact would not be ordinary waves in any sense. The energy transfer from the impact to the water creates what researchers describe as rim waves and collapse waves, both of which behave differently from the tsunami waves generated by undersea earthquakes, which are already capable of extraordinary destruction. The initial waves radiating outward from the impact point in all directions would be enormously tall, close to the impact site, potentially hundreds of meters high at the source. As they travel outward across the ocean, they decrease in height but increase in their geographic reach, spreading like rings from a stone thrown into a pond, but rings that carry the energy of thousands of nuclear warheads. The exact dimensions of the waves depend heavily on the depth of the water at the impact point, the angle of impact, the specific geometry of the ocean floor nearby, and the distance to various coastlines. A simulation of an Apophis splashdown in the Atlantic Ocean off the coast of Portugal produced estimates of a 4-metre-high wave striking a significant portion of the Portuguese coast. That simulation assumed a specific impact point and a specific set of conditions. Different impact points would produce different results. An impact in the centre of the Pacific Ocean would send waves toward Japan and the Philippines and Hawaii and the west coasts of North and South America simultaneously. An impact in the Indian Ocean could affect the coastlines of India, Bangladesh, Myanmar, Thailand, Indonesia, East Africa, and the Arabian Peninsula in a matter of hours. The 2004 Indian Ocean tsunami, one of the deadliest natural disasters in recorded history, killed more than 220,000 people. It was generated by a massive undersea earthquake, a seismic event that released energy equivalent to roughly 25,000 nuclear weapons, and it produced waves that reached heights of 30 meters in some coastal locations. An Apophis ocean impact would be a fundamentally different kind of event, releasing far more energy at the source, potentially generating waves of much greater initial height, and doing so without any of the gradual build-up that allows seismograph networks to provide warning. From the moment of impact to the arrival of the first waves on nearby coastlines might be a matter of minutes rather than the hours that the 2004 tsunami warning systems managed to generate in some cases. The geography of ocean strike makes for a different calculus of devastation than the geography of land strike. A land strike kills primarily the people near the impact zone. An ocean strike potentially endangers the populations of every coastline within a vast arc of ocean, people who might be thousands of kilometers from the impact point, and who might never have felt the heat of the fireball or heard the sound of the impact, but who nonetheless find their cities and villages and ports and beaches consumed by a wall of water they may have had little practical ability to evacuate ahead of. The good news, to the extent that there is any good news in a conversation about a 370-metre asteroid hitting the ocean, is that the water absorbs a significant portion of the asteroid's energy. The ejector that goes into the upper atmosphere is primarily water vapour and steam, rather than pulverised silicate rock, which means the stratospheric dust loading is lower than it would be for a land strike of equivalent energy, and the climate effects are therefore less severe and shorter lived. The bad news is that the tsunami risk extends around the entire ocean basin in ways that a land strike simply does not. Every coastal city within range, every low-lying delta, every port and fishing village and tourist beach and naval base on the shores of the affected ocean is in the path of what comes. And in the modern world, a very large fraction of the human population lives within a few kilometers of the coast. The third story is the airburst. The possibility that the asteroid enters the atmosphere at a shallow angle and begins to break apart before reaching the surface, releasing the bulk of its energy as an explosion in the air rather than an explosion on the ground. This is what happened at Chelyabinsk in 2013, when a rock estimated at roughly 18 to 20 meters across entered the atmosphere at a low angle over Russia and exploded approximately 30 kilometers above the city, releasing energy equivalent to approximately 500 kilotons of TNT, 30 times the yield of the Hiroshima bomb, and injuring roughly 1,500 people and damaging 1,700 buildings without leaving any crater at all. Apophis is 18 times larger in diameter than the Chelyabinsk object. Because energy scales with the cube of size, a scaling that is a rough approximation but a useful one, an Apophis airburst would be on the order of several thousand times more energetic than Chelyabinsk. The overpressure wave from an airburst of that magnitude at an altitude of, say, 20 to 40 kilometers would be capable of devastating an enormous region of the surface below it, potentially comparable in ground-level effects to a landstrike, though without the localized crater and with a wider geographic distribution of the blast effects. In some respects, an airburst might be more dangerous to a large population than a landstrike, because the energy is distributed over a larger area rather than concentrated at a single point. The Tunguska event was an airburst, and it destroyed more than 2,000 square kilometers of forest. An Apophis airburst would be roughly 100 times more energetic than Tunguska. There is, however, a further complexity. Whether Apophis would airburst or survive to the ground depends on its composition and structure, and while we know something about its bulk properties from spectroscopic observations, we do not know its internal structure well enough to predict its behavior in the atmosphere with high confidence. One of the things that OSIRIS-APEX will help establish, as it studies the asteroid in detail for 18 months starting in April 2021, is the composition and mechanical properties of Apophis in a way that would allow future researchers to model its atmospheric behavior much more accurately. That knowledge, gathered during the actual close approach, will be one of the most important pieces of data the mission returns. But in our hypothetical, in the story we are telling tonight, we are going to leave the specific scenario partly open. Whether Apophis strikes the ground or the ocean or explodes in the air, the scale of the event is the same, the energy is the same, the immediate hours and days that follow are shaped by the same physics. What changes with each scenario is the geography of suffering, the specific distribution of where the damage falls and who bears it. All three scenarios converge on the same set of questions afterward. What happens in the hours and days following the impact? How does a civilization of 8 billion people respond to something unprecedented in recorded history? And what does the world look like 1 year, 5 years, a generation later? Let us follow the aftermath into the dark. The days that follow a land strike have a particular quality in the imagination that is worth dwelling on, because it is in the days, and not the seconds, that the true scale of what has happened becomes comprehensible to the people who are far enough away to survive it, and who are now watching the news coverage trying to make sense of what they are seeing. In the immediate hours after impact, the visual record is fragmentary. Cameras in the periphery of the affected region capture the flash and the rising column of debris and smoke that climbs into the stratosphere, like a bruise spreading across the sky. Satellites passing overhead return images of an enormous cloud, bright white at the top where the material has been injected into the upper atmosphere, and dark and churning below where the fires are still burning and the dust of pulverized rock is still settling back to the surface. The scale of the cloud is the first thing that makes the full reality clear, because at satellite altitude you can see at a glance that this cloud covers a geographic area larger than most countries, and that what is underneath it is a landscape that no longer looks like any landscape that anyone has seen before. Closer in, the visual record is stranger and more disturbing. The aerial reconnaissance footage that military aircraft return in the first 12 to 24 hours shows a zone of absolute destruction that gives way to a zone of severe damage that gives way, at increasing distance, to a zone of damage that is heavy but patchy, and then to a zone where buildings are standing but windows are shattered, and roof tiles are displaced and people are sitting in the streets because something made the inside of every structure feel unsafe, and the instinct said go outside. The boundary between each zone is not a sharp line but a gradient. the severity of damage decreasing gradually as distance increases, until at some point on the outer edge the only sign that something catastrophic happened a few hundred kilometers away is a thin layer of grey-brown dust on every horizontal surface, a reduction in the apparent brightness of the sky, and a faint smell of something chemical and ancient in the air that people who have never smelled anything like it struggle to describe. The strangest element of the days following an impact, the element that does not map onto any previous disaster in human experience, is the astronomical one. Because the cloud of material ejected into the stratosphere by the impact does not stay over the impact zone. It spreads. The stratospheric winds, which blow at different speeds and in different directions at different altitudes, catch the fine particles and carry them laterally across the globe, and within days the sunsets at locations thousands of kilometers from the impact site begin to change. They become richer and more vivid, the same optical effect that produces brilliant red sunsets after major volcanic eruptions, as the particles scatter the shorter wavelengths of light and allow the longer red and orange wavelengths to dominate. People who have no other sign of what has happened notice that the sunsets are beautiful in a way they have not been before, and some of them, the ones who have been following the news, understand with a certain chill what is making them beautiful. This atmospheric signature, the stratospheric loading of fine particles that produces vivid sunsets and a slight reduction in direct solar radiation over weeks to months, is one of the measurable global signals of an impact event. It is not catastrophic at the scale Apophis would produce. It is temporary and recoverable. But it is the physical signature of the event written in the atmosphere, the mark that the impact has left on a planetary system that is much larger than the impact zone itself, the reminder that what happened in one specific place on one specific day has connected itself to the whole globe through the medium of the air and the light. It is also, in a quieter way, beautiful. And that beauty is real, even as what produced it was devastating. The universe has a habit of making beautiful things out of violent processes. The same forces that end things begin things. The same energy that destroys in one form creates in another. The ring nebula in Lyra, visible through even a small telescope as a pale, ghostly circle of glowing gas, is the remnant of a star that exploded thousands of years ago in a detonation that would have sterilized every planet in the nearby solar system. It is one of the most photographed objects in the sky. It is extraordinarily beautiful. It is made of death. The sunsets in the weeks after an Apophis impact would be the same kind of thing. The visible, transient, accidental beauty of a catastrophic process writing itself in light. The hours immediately following an Apophis impact would be, in certain respects, unlike any event in recorded human history. This is worth establishing carefully, not as hyperbole, but as a factual observation about what recorded history contains. Recorded history contains accounts of major earthquakes. It contains accounts of volcanic eruptions that darken the sky for years. It contains accounts of floods that killed hundreds of thousands of people, and famines that killed millions, and pandemics that reshaped the entire trajectory of civilizations. But it does not contain a single verified account of an impact by an asteroid of this size on an inhabited world. The geological record contains the evidence of such impacts, the craters and the iridium layers and the mass extinction boundaries that mark the moments when the universe sent something large enough to matter into our planet's path. But recorded human history, the last several thousand years of documented human experience, contains nothing like what we are describing. It would be entirely new, and that newness would itself be one of the most profound aspects of the event, because human societies respond to things they have categories for, things they have seen before or at least read about in sufficient detail to draw analogies from, and an Apophis impact gives them nothing familiar to hold on to. In the first minutes after the impact, the immediate response would be driven primarily by the most basic human functions: survival, communication, and the frantic attempt to understand what had just happened. In the impact zone itself, the question of response is largely academic, because within the innermost radius of devastation, there is no communication infrastructure to speak of, no surviving emergency services, no functioning government apparatus. The blast and heat and shockwave have been comprehensive. People who are in buildings within the most severely affected zone are dead or severely injured. People who are outside are almost certainly dead. The landscape within tens of kilometers of the impact point does not look like a disaster zone in the ordinary sense. It looks like something that has been subjected to conditions that are not part of any human reference framework. Beyond that innermost zone, at distances of 50 to 200 kilometers from the impact depending on terrain and the specific energy release, the situation is catastrophic but not total. Buildings have been damaged, some severely, windows have been shattered across enormous areas, fires have broken out, and many people are injured from glass and structural collapse and the secondary effects of the pressure wave. But people are alive, and their survival instinct and their communication instinct activate simultaneously. Phones are pulled out. Emergency calls are made or attempted because the cellular networks are overwhelmed immediately by the sheer volume of simultaneous calls. Social media platforms receive a flood of posts and videos from people who are far enough from the impact to have their devices intact and close enough to have captured something extraordinary. The footage spreads globally within minutes because the internet, despite its physical infrastructure being damaged in the immediate impact zone, remains functional across most of the planet for the first hours of the event. Governments activate their emergency response systems. In every country with a functioning national emergency management apparatus, the protocols that have been developed over decades of preparing for large-scale natural disasters begin to execute. Military assets are redirected toward the affected region. Federal emergency declarations are issued. Air traffic is suspended over the affected airspace. International communications begin almost immediately, because an event of this scale crosses national borders in its consequences regardless of where the initial impact occurs, and the international coordination mechanisms built over the previous decades begin to activate. The United States Federal Emergency Management Agency, the European Union's Civil Protection Mechanism, national emergency management agencies across every affected country, all of them operating simultaneously, all of them working from plans and protocols that were never designed for this specific scenario, but that have enough flexibility and enough trained personnel to begin organising a response. The military assets that move first are search and rescue teams, medical units, engineering battalions equipped to clear debris and restore access routes. The civilian infrastructure, the hospitals and emergency departments and first responder networks in the regions adjacent to the impact zone, begins to receive the first wave of injured survivors within hours. In the days that follow the immediate crisis of the first hours, the broader picture of what the impact has done begins to emerge through satellite imagery, through the reports of reconnaissance aircraft, through the accounts of people who are in the affected region and have managed to reach communications infrastructure outside it. The picture that emerges is, inevitably, worse in some respects and better in others than the initial estimates. Worse, because the full geographic extent of the affected area takes time to establish and is almost always larger than the first assessments suggest. Better, because the survival instinct of human populations is more robust than worst-case planning models can capture, and because the communities adjacent to the devastated zone respond to the presence of survivors with the resources and energy that disasters consistently reveal in human populations given the opportunity to act. The international response to an Apophis-scale impact would dwarf any humanitarian response in recorded history. The aid flows, financial, material, personnel, that followed the 2004 Indian Ocean tsunami, which killed more than 220,000 people and displaced millions more, were the largest in the history of international disaster relief up to that point. An Apophis impact killing millions of people and devastating a region potentially the size of a small country would trigger a response on a scale that the international humanitarian system has never before been asked to execute. Supplies, medical teams, search and rescue personnel, engineering assets, military logistics, all of it flowing toward the affected region from dozens of countries simultaneously, coordinated through the United Nations Office for the Coordination of Humanitarian Affairs and a dozen other international bodies whose systems would be pushed to their absolute limits. For the broader global economy, the consequences of an Apophis impact would extend far beyond the immediate affected region. Global financial markets would experience shocks of a kind not seen since the Great Depression, as the immediate uncertainty about the scale of damage, the damage to global supply chains, the impact on specific industries tied to the affected geography, and the sheer psychological effect of an event with no modern precedent rippled through interconnected markets simultaneously. Insurance companies would face claims of a magnitude the industry has never processed. Supply chains that pass through or near the affected region would be disrupted for months or years. But the global economy would not collapse. This is one of the important conclusions of serious analysis of impact consequences at this scale. A 370-meter impactor is devastating and historically unprecedented, but it is not civilization-ending. Human civilization survived the Black Death, which killed roughly a third of Europe's population in the 14th century. It survived the two world wars, which together killed somewhere between 70 and 85 million people, and destroyed the physical infrastructure of multiple major nations. It has survived pandemics, droughts, famines, and the sustained violence of colonial exploitation. An Apophis impact would be, in terms of immediate casualties, comparable to some of the worst disasters in human history, and in terms of the physical destruction of a specific region, it would be unprecedented. But the bulk of humanity's infrastructure, knowledge base, industrial capacity, agricultural capacity, and political organization would survive intact. The world goes on, damaged, grieving, and transformed by the experience, but going on. 1 year after the impact, the affected region is still in the process of recovery, but the nature of that recovery has shifted from the initial emergency phase to the slower, more complicated work of reconstruction. The debris has been cleared from the areas of the impact zone that are being reclaimed. The most severely affected areas, the innermost circle of the impact, may not be reclaimed for years or decades, both because of physical conditions and because of the psychological weight of what happened there. Something like this happened with the exclusion zone around Chernobyl, which 30 years after the nuclear disaster remains largely uninhabited, less because it is physically impossible to live there, and more because of the combination of real hazard, complicated bureaucracy, and the particular quality of emptiness that certain places acquire after catastrophic events. The political consequences of the impact at 1 year out are beginning to clarify. There is, in every serious analysis of this question, one political consequence that emerges with near certainty from any asteroid impact that produces significant casualties and damage. The funding for planetary defense goes up. Not a little. Not by the incremental amounts that characterize normal scientific budget processes. The funding goes up by orders of magnitude, driven by a political will that simply did not exist before the impact, and that exists afterward with an intensity that is difficult to overstate. Because the one thing that an asteroid impact demonstrates more forcefully than any argument that planetary scientists have ever made in a budget hearing is that the threat is real, not theoretical, not a remote possibility to be weighed against other budget priorities. Real. It happened, and it can happen again. We will come back to what the world has been doing about that possibility. For now, we're going to step back from the specific geography of the event and place Apophis in the longer context of the record of things that have hit Earth across the span of deep time, because that context is essential for understanding what an Apophis impact actually means in the history of life on this planet. To understand where Apophis sits in the history of things that have struck this planet, you need to travel backward through time in a way that modern astronomy and geology have made possible, with a precision that would have seemed miraculous to any previous generation of humans. We can read the history of cosmic impacts in the rocks, in the layers of sediment, in the shapes carved into the landscape of every continent and ocean floor, and that record tells a story that is simultaneously terrifying and strangely reassuring. The universe has been throwing things at Earth for as long as Earth has existed, and life has been surviving those impacts for nearly that long. The most immediate reference point in living human memory is the Chelyabinsk event of February 15, 2013. On that morning, a rock estimated at approximately 18 to 20 meters across entered the atmosphere over the Russian city of Chelyabinsk, traveling at roughly 19 kilometers per second, and exploded approximately 30 kilometers above the surface in an airburst that released energy equivalent to about 500 kilotons of TNT. The explosion generated a shockwave that broke windows across an area of nearly 2 million square kilometers. More than 500 people were injured, mostly from glass. Roughly 7,200 buildings sustained some form of damage. The footage was captured on hundreds of dashboard cameras and security systems, and it circulated globally within hours, giving humanity its clearest real-time view of what a small asteroid impact looks like from the ground. It was breathtaking and terrifying, and in the context of what we have been discussing tonight, it was tiny. The Chelyabinsk object was tiny. An object 1/30th the diameter of Apophis, carrying 1/100th of 1% of Apophis's energy, was enough to injure 1/500 people and damage millions of buildings across an enormous swath of Russia. Scale that up to Apophis, and you begin to understand what 200 megatons actually feels like on the surface of a populated planet. 15 years before Chelyabinsk on June 25, 1998, astronomers discovered what appeared briefly to be an asteroid on an impact trajectory with Mars. It turned out to be a prediction error, but the incident highlighted the frequency with which near-Earth objects make their presence known. Between those events and extending back through the century, there were dozens of smaller events. The Park Forest meteorite of 2003, the Alma-Ata impact of 2008, the Vitim event of 2002, all of them small, all of them producing no casualties and minimal damage, all of them serving as reminders that the inner solar system is not empty, and that things hit Earth on a regular basis at sizes below the threshold of catastrophe. A century before Chelyabinsk on June 30, 1908, something struck the Podkamennaya Tunguska river region of Siberia. The object, estimated at between 50 and 80 meters across, was probably a stony asteroid or possibly a comet fragment. It never reached the ground. Instead, it exploded in the atmosphere at an altitude of roughly 5 to 10 kilometers, releasing approximately 10 to 15 megatons of energy in a single instant. The explosion flattened approximately 2,000 square kilometers of forest, roughly 80 million trees brought down in a few seconds by the shockwave. The area was so remote that there were no confirmed human casualties, though the event was felt and heard at distances of hundreds of kilometers. If the same object had struck a few hours earlier or later, as the rotation of the Earth brought different geographies under the asteroid's path, it might have struck a major European city. St. Petersburg is one of the cities that would have been in the path under slightly different timing. The death toll in that scenario would have been measured in the tens of thousands. Beyond Tunguska, the record gets harder to read because the evidence is geologic rather than historical. The Barringer crater in Arizona, a nearly perfectly circular hole in the desert floor roughly 1.2 kilometers across and 170 meters deep, was created approximately 50,000 years ago by an iron meteorite perhaps 50 meters in diameter. The impact released energy equivalent to approximately 10 megatons of TNT and threw about 175 million tons of rock out of the crater in a fraction of a second. In 50,000 BCE, the site was probably uninhabited, or at most sparsely populated by early humans who left no written record of the event. But the crater survived, perfectly preserved in the dry Arizona desert, as a physical monument to what happens when even a relatively small piece of cosmic debris hits the ground at hypersonic velocity. Moving further back through time, the impacts grow in scale and in consequence. The Chesapeake Bay, that distinctive indentation in the eastern coastline of the United States that separates the Delmarva Peninsula from the rest of Virginia and Maryland, sits in the center of what was once a much larger bay and harbor system. The reason the bay exists at all, the reason the geology and geography of that region look the way they do, is that approximately 35 million years ago, an asteroid or comet roughly 2 to 3 kilometers across struck the shallow ocean that covered the eastern edge of the North American continent. The impact created a crater roughly 85 kilometers across. It disrupted the local geology so thoroughly that the effects are still measurable in the sediment layers beneath the modern bay. The shoreline of the eastern United States is partially the product of a rock that fell from space 35 million years ago. And at the far end of the scale of recorded impacts, the event that has defined our understanding of what cosmic impacts can do at their most extreme, the Chicxulub impact of 66 million years ago. The rock that ended the Cretaceous period and, along with the volcanic activity of the Deccan Traps in what is now India, triggered the mass extinction that eliminated 3/4 of all species on Earth, including every non-avian dinosaur. The Chicxulub impactor was approximately 10 to 15 kilometers across. It struck the shallow seas of what is now the Yucatan Peninsula in Mexico, in a location that maximized the amount of sulfur-rich rock it vaporized, which in turn maximized the sulfur content of the stratospheric aerosol cloud that formed over the following hours and days and began blocking sunlight across the globe. The crater it produced, now buried under kilometers of sediment and ocean water, is approximately 180 kilometers across. The energy of the impact was roughly 100 million megatons of TNT. Not 200 megatons like Apophis, 100 million megatons, a number so many times larger than Apophis's energy budget that it barely makes sense to put them on the same scale. Apophis, at 370 meters, sits between the Barringer crater impactor, which was roughly 50 meters across, and the Chicxulub impactor, which was roughly 10,000 meters across. In terms of energy, Apophis releases about 1,200 megatons compared to Tunguska's 15 megatons, and Chicxulub's 100 million megatons. It is vastly more energetic than anything in recorded human history, and vastly less energetic than the impact events that have reshaped the biosphere. It sits in a zone that planetary scientists sometimes call the regional catastrophe range. Too small to threaten the global biosphere and civilization as a whole, large enough to devastate a region the size of a small country or a large city, and kill a significant fraction of its population. There is another comparison that is rarely made but that I think belongs here, and it concerns time. We tend to think of asteroid impacts as rare events, things that happen on geological timescales, and that we are therefore unlikely to encounter in our own lifetimes. And for the largest impacts, the civilization-threatening ones, that is broadly true. An object large enough to end industrial civilization strikes Earth roughly once every 100 million years on average. We are probably safe from that scale of event for the foreseeable future, but at Apophis's scale, at the scale of objects between 100 and 500 meters across, the frequency is much higher. Objects of this size are estimated to strike Earth roughly once every 10,000 to 80,000 years. The Apophis flyby of 2029 is not a once-in-a-billion-years event, it is a once-in-a-few-thousand-years event, on the timescale of human civilization, which is only about 5,000 to 10,000 years old depending on how you measure it. That means an impact of this magnitude has probably occurred somewhere in the world during the span of recorded history, and either struck an uninhabited area or left evidence we have not yet connected to its cosmic cause. The Holocene era, the geological epoch in which all of recorded human civilization has taken place, has not been impact-free. It has simply been lucky, in the sense that the impacts that have occurred have largely fallen in places and at times that did not produce consequences that made it into the historical record in a recognizable form. That luck is not infinite. It is not a guarantee. And one of the most important things that modern astronomy has done beginning in the 1990s with the first systematic surveys for near-Earth objects, and continuing with increasing sophistication to the present day, is to replace the passive reliance on luck with the active practice of watching. Let us talk about that watching. Let us talk about what we have built, and who is doing it, and what it means that we are the first civilization in the history of this planet with the capability to see the serpent coming before it arrives. There are people, right now, as you're reading this, who are doing something that has no real precedent in the history of life on Earth. They are watching the sky in a systematic, comprehensive, institutionally funded way, specifically for the purpose of finding things that might hit us. Not watching the sky for weather, not watching it for navigation, not watching it to understand the stars or measure the distance to other galaxies, or probe the early universe for the echo of the Big Bang. Though all of those things are happening simultaneously in observatories and radio dishes and space-based telescopes around the world. Watching it specifically, methodically, and with urgency for rocks on collision courses with the planet. The Catalina Sky Survey, operating from telescopes on Mount Bigelow and Mount Lemmon in the Santa Catalina Mountains of Arizona, discovers more near-Earth objects per year than any other survey on the planet. It runs every clear night, scanning the sky in a systematic grid pattern designed to cover as much of the ecliptic, the plane of the solar system where near-Earth asteroids are most commonly found, as possible during the night hours available. The images it takes are processed automatically by algorithms trained to identify moving points of light against a fixed background of stars, and the candidates those algorithms flag are reviewed by human analysts who determine whether they are genuine asteroid detections or false positives generated by cosmic rays or satellite trails or instrumental artifacts. The genuine detections are reported to the Minor Planet Center, combined with any other observations from other observatories, and used to calculate and refine orbital predictions. The Pan-STARRS system, operated by the University of Hawaii from the summit of Haleakala on Maui, adds additional capacity to the global network. The ATLAS system, the Asteroid Terrestrial Impact Last Alert system, operates from 4 telescopes on 2 different continents and is designed specifically to provide warning of impactors in the smaller size ranges, objects between 10 and 100 meters across that other surveys might miss, because they are looking for larger objects, and because objects this small are faint enough to be difficult to detect at the distances where useful warning time might still be available. ATLAS completed its planned global expansion with additional telescopes in South Africa and Chile in 2022, giving it coverage of the entire sky that is not accessible from the northern hemisphere. And then there is the Vera C, Rubin Observatory, perched on a mountain in northern Chile and representing the single most significant advance in ground-based survey astronomy in a generation. Its primary mirror is 8.4 meters across, larger than most research telescopes in history, and it is coupled with the largest digital camera ever built, a 3.2 gigapixel sensor capable of imaging a patch of sky, roughly 49 times the area of the full moon, in a single exposure. It will survey the entire available southern sky every 3 nights, generating a data volume so enormous that the algorithms and computing infrastructure required to process it represent their own engineering challenge. In its first 7 nights of operations in late 2025, the Rubin Observatory discovered an enormous, record-breaking asteroid that previous surveys had missed, and that discovery alone justified years of planning and construction. When it reaches full operational capacity, it is expected to increase the known catalogue of near-Earth objects by a factor of roughly 10 over its 10-year survey mission. Beyond ground-based surveillance, the planetary defense community has for years advocated for a dedicated space-based infrared survey telescope. Infrared wavelengths are better suited to detecting dark asteroids, objects whose surfaces absorb rather than reflect visible light, and that are therefore much harder to find with optical telescopes that rely on reflected sunlight. The DART mission in 2022, which successfully changed the orbit of the asteroid Dimorphos by deliberately crashing a spacecraft into it at 6.6 kilometers per second, demonstrated that kinetic impactor deflection works, that we can move an asteroid if we know it is coming and have enough time to respond. That mission changed the orbit of Dimorphos by roughly 33 minutes, modifying its orbital period around the larger asteroid Didymos from 11 hours and 55 minutes to 11 hours and 23 minutes. The margin that deflection requires is not large. A small nudge applied years or decades before an impact date can move an asteroid just enough that it misses Earth entirely. Because the Earth is a relatively small target in an enormous volume of space, and the precision required to strike it as opposed to passing near it is considerable. But deflection requires warning time. DART demonstrated that kinetic impactor deflection is feasible for an asteroid of Dimorphos' size, roughly 170 meters across, given a notice period of several years, and the resources required to build and launch a spacecraft. Apophis, at 370 meters, is larger and therefore harder to deflect with a single kinetic impactor, but multiple impacts, or a gravity tractor mission that uses the gravitational attraction between a spacecraft and an asteroid to gradually alter the asteroid's path over years, could in principle achieve sufficient deflection if the notice period was measured in decades rather than years. The notice period is the key variable, and that is what the survey telescopes are providing. Every asteroid discovered 10 or 20 or 50 years before it might pose a threat is an asteroid that has given humanity the time to assess, plan, and if necessary act. Every asteroid that goes undiscovered until it is already inside the orbit of the Moon gives humanity hours of warning and no practical options. Apophis, discovered in 2004 with a 2029 encounter date, gave the planetary science community 25 years of warning. 25 years to refine the orbital prediction, reduce the uncertainty, and ultimately determine with certainty that the 2029 approach would be a miss. Had the initial 2004 probability of 2.7% been confirmed, and had the asteroid been on a genuine impact trajectory, 25 years would have been more than sufficient time to mount a deflection mission. The cost of such a mission, in human lives and financial resources, would have been vastly less than the cost of failing to deflect it. This is the economic and moral case for planetary defense in its most compressed form. Finding asteroids early enough to act costs billions of dollars over decades. Deflecting an asteroid that is on an impact trajectory, given sufficient warning time, is technically feasible with technologies we already have. Failing to deflect an Apophis-scale impactor costs potentially millions of lives and trillions of dollars in damage and recovery. The math is not complicated. The planetary defense community has been making this argument in budget hearings for decades, often with limited success, because the challenge of funding against a risk that feels remote and theoretical is one that democratic political systems struggle with structurally. It is much easier to fund responses to disasters that have already happened than preparations for disasters that might happen in the future. An actual impact, even one that was significantly smaller than Apophis, would transform that political calculus overnight. The willingness to spend what it takes to find every significant near-Earth object and to have deflection options ready to deploy on short notice would become, in the aftermath of a major impact, politically impossible to oppose. The tragedy is that the lesson is so expensive. The lesson that the Chelyabinsk event provided in 2013, when a rock 20 meters across injured 1,500 people and damaged millions of buildings without even reaching the ground, was taught at a relatively low cost in human suffering. It did not have the political staying power to significantly accelerate planetary defense funding in most of the countries that watched the footage. The lesson of an Apophis-scale impact would be taught at a far higher cost, and it would be far harder to forget. But here is the thing that the story of planetary defense ultimately comes to, the thing that sits underneath all the specific technical and political details and gives them their deepest meaning. We are not helpless. That is the sentence that distinguishes us from every generation of humans that came before us, and from every other species that has ever lived on this planet. Every impact that struck Earth before the invention of modern astronomy struck a world that had no warning and no recourse. The organism in the path of the impact had no information that it was coming. It could not calculate the trajectory. It could not estimate the probability. It could not redirect the object, evacuate the impact zone, prepare countermeasures, or do anything at all except exist in the path of the impact and be affected by it in whatever way the physics determined. Life on Earth has been struck by objects of every conceivable size for 4 billion years, and for 4 billion years it has had no agency in the matter whatsoever. We are the first exception. We are the first form of life on this planet with the capacity to look up, identify the approaching danger, calculate its trajectory, assess its likely consequences, and in at least some scenarios, do something about it. That capability is new. It is only a few decades old in its serious institutional form. It is incomplete and underfunded, and it has significant gaps that would need to be addressed before we could claim with confidence that we can find and respond to every impactor of every size with every possible notice period. But it exists, it is real, and it is growing. The watch is kept. Not by priests burning wax figures in the temple courtyard, not by rituals designed to strengthen Ra for his nightly battle with the serpent, but by engineers writing algorithms to process terabytes of nightly sky images, by radar operators pointing dishes at passing asteroids to measure their positions to within meters, by spacecraft that have already left the Earth on their way to study and ultimately to touch an asteroid that will pass our planet in April 2029. The serpent has a name, we know its orbit. We know its size and its shape and its composition and its trajectory for the next 100 years. And in April 2029, 3 spacecraft will be riding alongside it as it makes its extraordinary close pass of our world, studying it, measuring it, learning everything we can from the visit that could become indispensable knowledge the next time something less certain than Apophis is found heading our way. That is the watch, and it is keeping it. We have travelled a long way tonight, from the temples of ancient Egypt to the depths of the solar system, from the discovery of a 370-metre rock in the night sky over Arizona, to the physics of what happens when 1,200 megatons of energy meets the surface of an inhabited planet, from the immediate chaos of the first hours after impact to the long geological record that places all of this in the context of the 4 billion-year story of a planet being struck again and again by the debris of its own formation. It is a long way to have travelled. But there is something we have not yet addressed, something that has been waiting underneath all of the science and all of the history, something that I think is the real question that all of this points toward. The real question is not what Apophis would do to the surface of the Earth. We know that. The science is clear and the numbers are specific, and the consequences, while severe, are bounded and survivable and ultimately recoverable. The real question is what it would mean. What it would mean for a civilization to be confronted for the first time in its history with incontrovertible physical evidence that the sky is not neutral, that the universe is not arranged around our comfort and survival, that the cosmos we inhabit contains forces that operate at scales entirely indifferent to whether we exist or not. Not as an abstract philosophical proposition, not as a claim in a theology or a speculation in a scientific paper, as a fact, as a smoking crater somewhere on the surface of the world, visible from orbit, measurable in seismographs halfway around the planet, felt as a shockwave in the bones of every person within hundreds of kilometers. Human civilizations have been confronted with large-scale disasters before. Earthquakes have leveled cities, floods have consumed entire valleys, famines have depopulated regions, pandemics have killed fractions of entire continents, volcanic eruptions have buried cities under ash and sent enough material into the stratosphere to cool the climate for years, as the eruption of Tambora in 1815 did, producing what was known in the affected northern hemisphere as the year without a summer and contributing to crop failures that killed tens of thousands of people. None of those events were generated by a force that had nothing to do with Earth's own internal dynamics. They were all, in one sense or another, products of the planet itself, events arising from the tectonic activity or atmospheric dynamics or biological interactions of the world we live in. Terrible, yes. Unprecedented in scale for the people who experienced them, often yes. But comprehensible at some level as things that Earth does. An asteroid impact is different in a way that is difficult to articulate precisely, but that matters enormously for how we would process it. An asteroid impact comes from outside. It comes from a part of the universe that has nothing to do with us. From an object that has been pursuing its own orbit around the Sun for 4.5 billion years entirely, without regard for whether anything alive was living in its eventual path. It is not a product of the planet's anger, or God's judgment, or any force that can be attributed to something that cares about us one way or another. It is the universe operating according to its own physics, in its own time, and the fact that one of its operations happens to intersect with our planet is, from the universe's perspective, not a fact of any significance whatsoever. The ancient Egyptians could not tolerate that kind of indifference. Nobody can, really, which is why the mythology they built gave the darkness a personality, a motivation, a hunger. Apophis wanted to eat the sun. Apophis was the enemy, and if the enemy could be named, it could be fought, and if it could be fought, then the battle mattered, and if the battle mattered, then the outcome was not simply a matter of physics, but of moral weight. The side of light and order was supposed to win, had to win. The priests said so. The rituals confirmed it. The sun rose every morning as proof. We do not have that mythology anymore. Most of us, anyway. What we have instead is science, which offers something both more and less comforting than a cosmic battle between good and evil. Less comforting because the universe that science describes does not take sides. There is no force of order opposed to Apophis. There is only orbital mechanics, and the orbital mechanics do not care which way they resolve. More comforting, perhaps, because science also tells us something the Egyptians did not know, that the outcome is not entirely beyond our influence, that the watch can be kept with instruments that are actually capable of seeing the danger in time to respond to it, that the serpent can be found and named and tracked, and, if we have the resources and the will, redirected before it arrives. But the science cannot resolve the deeper question, which is not what we can do about an asteroid, but what it means to live in a universe where asteroids exist, where the solar system contains right now an estimated 25,000 near-Earth asteroids larger than 140 meters, of which we have found and catalogued roughly 40%, which means that roughly 15,000 significant near-Earth asteroids remain undetected, where the same processes that built the planets and delivered water to early Earth and contributed the organic chemistry from which life eventually emerged also continue to produce, occasionally, the kind of close encounter we have been discussing tonight, where the history of life on this planet is inseparable from the history of impacts, because without the delivery of water and organics by early comets and asteroids there might be no life at all, and without the Chicxulub impact there would be no mammals in the ecological positions they currently occupy, and without all the smaller impacts scattered across geological time, the evolution of life would have followed different paths that we cannot trace because they did not happen. There is a version of this thought that feels like a cosmic indignity. The idea that we are here, partly because of the random violence of the solar system, that our existence depends on a series of impacts that happen to fall in the right places at the right times, to create the conditions life needed, and to clear the ecological space that mammals eventually filled. The dinosaurs, who by all accounts were extraordinarily successful and might have continued their reign for another 100 million years, died because a rock fell from space at the wrong angle, or the right angle depending on your perspective, since their death made room for the mammals that eventually made room for us. It is the largest example in natural history of what might be called the butterfly effect, the sensitivity of complex systems to tiny changes in initial conditions, except that the butterfly here was 10 kilometers across and the effect was the extinction of 3/4 of all species on Earth. But there is another version of the thought that feels less like indignity and more like something approaching awe. The universe in its operations produces catastrophe and opportunity simultaneously. The same force that killed the dinosaurs created the conditions for human intelligence. The same solar system processes that occasionally send rocks into planetary surfaces also built those planetary surfaces in the first place, delivering the material that became the continents and the oceans and the atmosphere and the biosphere. The violence of the solar system's history is not separate from its generativity. It is the same thing, operating at different times and different scales. And we, the species that emerge from all of that, are doing something genuinely new with the awareness that comes from being intelligent and observant. We are looking back at the process that made us and saying, we can see what is coming next, and we have opinions about it, and we have the technical capability to do something about it. Not everything about it. Not the deep background cosmic violence of the early solar system, the period of heavy bombardment 4 billion years ago, when the inner planets were being struck by things thousands of times larger than Apophis on a regular basis. Not the eventual death of the Sun in roughly 5 billion years, but the specific calculable trackable threat of known asteroids on known orbits with known probabilities of collision in the coming centuries that we can address, that we are addressing. The Apophis of our hypothetical, the version of the rock that we imagined striking the Earth tonight, would in a strange sense have been the most useful catastrophe in human history. Because the one thing that an actual asteroid impact would produce, beyond the immediate devastation and the humanitarian crisis and the long work of reconstruction, is a species-wide change in how humanity relates to the fact of its own cosmic vulnerability. We already know that we are vulnerable. The astronomers have been saying so for decades, with increasing precision and increasing urgency, and the political will to respond has been frustratingly limited in most countries and in most budget cycles. An actual impact would not change the physics. It would change the psychology. It would transform the abstract awareness that impacts happen into the visceral, immediate, politically galvanizing knowledge that they happen to us, specifically in our lifetimes, with consequences we can see from space and measure in seismographs and count in the faces of the people who did not survive. Every civilization that has ever faced a catastrophic natural disaster has been changed by it in ways that outlast the disaster itself. The Black Death killed 1/3 of Europe's population, and in doing so broke the feudal system that had structured European society for centuries, created the labour shortage that gave surviving workers negotiating power they had never previously possessed, contributed to the breakdown of the Church's authority when the Church's prayers had no visible effect on the mortality statistics, and in the long view, accelerated the social changes that eventually produced the Renaissance and the scientific revolution. A disaster of unprecedented scale produces changes of unprecedented depth. An Apophis impact, the first cosmic impact on a modern civilized world, would be the beginning of something as much as it was the end of something. What that something might be is, perhaps, a species that finally takes seriously the full scope of its responsibility for its own survival, not just the short-term survival challenges of the next election cycle or the next economic quarter, but the long-term survival challenges of the next few thousand years, during which the catalogue of near-Earth objects will need to be completed, the deflection technologies will need to be developed and tested, the international cooperation frameworks will need to be built and maintained, and the basic infrastructure of a planet that can protect itself will need to be created from scratch, because it does not exist yet in anything like its necessary form. That is the work. It is enormous and unglamorous, and it requires sustained political will across generations and across national boundaries, in ways that human political systems are not currently optimized to provide. But it is the work, and it is being done slowly and with insufficient resources, by the people whose job it is to watch the sky and calculate the orbits, and run the simulations and publish the papers, and testify at the budget hearings, and make the case over and over again that the serpent is real and the watch must be kept. The ancient Egyptians burned their wax figures and recited their spells, and went to sleep believing that their vigilance was part of what kept the sun rising. They were not wrong about the underlying principle, only wrong about the mechanism. Vigilance matters. Attention to what moves through the dark matters. The watching is not separate from the protection. The watching is the protection, because an impact that has been found and calculated and planned for is an impact that might be deflected. And an impact that has been deflected is the greatest success story in human history that no one will know about. Because the disaster that was prevented is always invisible, always the thing that did not happen. You will not see in the newspapers the headline about the asteroid that missed us, because someone spent 40 years watching the sky, and $1 billion building the survey telescopes, and a decade designing the deflection spacecraft, and a year of orbital mechanics getting the trajectory right. You will see the sky in the morning, clear and ordinary, the sun rising as it has for the entire existence of this planet and as it will for billions of years more, and somewhere in the planetary science community there will be people who know why that morning is a little more certain than it would have been without the work, who know the name and the number and the orbital parameters of the object that passed by a slightly different path because of something they did, and who will go back to their desks and their telescopes and keep doing the work because there are others behind it in the catalogue and the work is never finished. The serpent can never be permanently destroyed. The ancient Egyptians understood that. It comes back every night, with the same coiling darkness and the same hunger for the light. The answer to that is not to stop fighting. The answer is to keep the watch. Rest now. The sky outside your window is being watched. The orbits are calculated, the telescopes are running. The serpent is known and named and tracked to within a few kilometers of its predicted position for the next 100 years, and the people whose job it is to know these things are at their desks, checking the numbers one more time, as they have been doing every night for years and will be doing every night for years to come. You can let the dark be the dark. It is watched dark, known dark, measured dark. The sun will come up. There is a specific quality to the 2 years between now and April 13th, 2029 that deserves its own attention. Because those 2 years are not simply a countdown to a close call. They're a period of preparation unlike anything the planetary science community has experienced before. A window of time during which everything that can be learned about Apophis before its encounter with Earth is being learned. Everything that can be built to study it during the encounter is being built, and everything that can be done to turn a near miss into an opportunity for knowledge is being done. The scientists who have spent their careers studying near-Earth objects and arguing for the resources to take planetary defense seriously are approaching April 2029 with something that resembles the feeling you have before the most important exam of your life, the feeling of wanting every remaining hour of preparation to count, of going over the material one more time not because you expect to fail, but because the stakes are high enough that you want to leave nothing unread. OSIRIS Apex is already en route. The spacecraft that spent years orbiting the asteroid Bennu, that carefully mapped its surface and extended its sampling arm to collect 120 grams of material from the asteroid's exterior and return that material to Earth in a sample canister that parachuted into the Utah desert in September 2023. That spacecraft is now burning its way across the inner solar system toward a rendezvous with Apophis. It carries instruments capable of analyzing the chemical composition of the asteroid's surface, cameras that can resolve features just a few centimeters across, and the remaining fuel from its Bennu mission that will allow it to make several close passes of Apophis's surface during the 18 months it plans to spend in close proximity. At some point during its study, it will fire its thrusters to disturb the surface of the asteroid, exposing the material beneath the weathered outer layer for analysis in a maneuver called a touch and go that it already successfully performed at Bennu. It will be the most intimate contact ever made between a human spacecraft and an asteroid of Apophis's size. Ramses is being built. The European Space Agency's Rapid Apophis mission for space safety is scheduled to launch in the spring of 2028 and is designed to arrive at Apophis ahead of its closest approach to Earth, giving scientists the opportunity to observe the asteroid's surface and rotation state before the encounter and then compare those observations to what they find afterward. The before and after comparison is scientifically invaluable because the question of how Earth's gravity reshapes the surface of a passing asteroid, the question of what tremors and landslides and rotation changes a close approach produces, can only be answered by a mission that sees both states. Ramses is that mission. Destiny Plus is Japan's contribution to the fleet, a spacecraft designed to study the dust environment around Apophis and to make detailed observations of its surface from a variety of angles and distances, it adds a third set of instruments to what will be the most intensively observed asteroid encounter in history, and the combination of data from 3 independent spacecraft operated by 3 space agencies with different technical traditions and different instrument philosophies will produce a picture of Apophis that is richer and more reliable than any single mission could achieve. 2 billion people on the ground will be watching too. In Europe, in North Africa, across the Middle East and into Western Asia, people who have never owned a telescope and may never have had particular interest in astronomy will find themselves looking up on the evening of April 13th, 2029, to see a point of light moving visibly across the sky, covering the apparent diameter of the Moon every minute, taking approximately 8 hours to cross the visible sky from horizon to horizon before disappearing. Some of them will have been following the story of Apophis for years. Others will encounter it for the first time when a news alert or a social media post tells them that something extraordinary is happening overhead right now, and all they have to do is go outside and look up. Both types of people will look up, and what they will see will not be terrifying, it will be beautiful. There is a strange comfort in this, in the idea that the rock that frightened the world for 17 years, that sat at level 4 on the Torino scale longer than any asteroid in history, that generated enough public anxiety to produce thousands of news articles and documentaries and what-if scenarios, and this very story will ultimately pass us by in a way that is visible and magnificent and open to 2 billion pairs of eyes simultaneously. The serpent will come, and the serpent will pass, and the world will be watching, and the world will not be destroyed. It will be educated. It will be given the most vivid possible demonstration that the solar system is not a dead and empty backdrop to human history, but an active and ongoing process in which we are participants, not merely observers, and that our participation, if it is thoughtful and sustained and adequately resourced, includes the participation of being able to change some of the outcomes. The lesson of Apophis, real Apophis, the Apophis that is going to pass 32,000 kilometers from Earth on a Friday the 13th in April 2029, is not primarily a lesson about danger, it is a lesson about discovery. We found the rock, we calculated its path, we confirmed its trajectory to within a few kilometers of predicted position. We determined it would miss us with certainty good enough to remove it from every risk list on the planet. We built 3 spacecraft to study it as it passes. We watched its discovery panic the world and then watched the science calmly, methodically, over 17 years of observation, bring the probability of impact to 0. That is not a story about how dangerous the solar system is. That is a story about how capable we are when we pay attention. Now let the attention rest. The story is told. The serpent has come and passed and will pass again in 2029 in the real world, safely, magnificently, watched by instruments and eyes in ways that the ancient Egyptians who first named it could not have imagined. The knowledge we will gather from the real Apophis encounter will be the most detailed study of a near-Earth asteroid ever conducted, and it will sit in the scientific literature for decades, informing every mission and every calculation and every planetary defense decision that follows it. The serpent in its passing will teach us how to deal with the next one. Close your eyes now. Let the numbers fade, the impact energies and crater diameters and orbital parameters and Torino scale ratings. Let all of it settle gently into the background like the sound of a river you've been walking beside for a long time, present but no longer demanding attention. The science is done for tonight. The hypothetical has played out and been considered, and now the mind can let it go. Let it drift into whatever space the sleeping brain uses for the things it has processed and filed away, and does not need to hold on to consciously anymore. Think instead of what tonight's journey has been about at its deepest level. It has been about watching, about the oldest human instinct, older than agriculture and older than cities and older than writing, the instinct to look at the sky and try to understand what is moving through it and what it means for the people below. Every civilization has done this. Every culture that has ever existed has pointed its most careful observers at the stars and charged them with making sense of what moves up there and what it signifies for the world below. The Egyptians built their mythology of Ra and Apophis from watching. The Greeks mapped the constellations from watching. The navigators who crossed the Pacific without instruments followed the stars from watching. Every generation of astronomers from Hipparchus to Tycho Brahe, to Caroline Herschel, to Vera Rubin, has added to the accumulated record of careful watching that makes our current understanding possible. And tonight, this specific night while you have been listening to this, while the story of Apophis unfolded in the space of the hour or hours you have been awake for it, somewhere in the world a telescope was pointing at a patch of sky and taking images, and an algorithm was comparing those images to the background of fixed stars, and a moving point of light was being flagged for human review. And a human being whose job it is to take this seriously was looking at the flagged candidate and deciding whether it warranted further observation. That is happening right now. It is happening every clear night at observatories on every inhabited continent. The watch is not a metaphor. It is a shift schedule and a software pipeline and a database of orbital elements and a network of researchers who talk to each other across time zones and who, between them, are responsible for knowing what is coming before it arrives. You are living in the first civilization in the history of this planet to have that capability. To know, with real certainty and real precision, the positions and velocities and future paths of thousands of objects in the solar system that would once have arrived without warning. To have already found the most famous near-Earth asteroid of our generation, watched it for 25 years, confirmed its safety, and dispatched 3 spacecraft to meet it when it passes. To have demonstrated, with DART in 2022, that we can actually move these things if we need to. These are new abilities. They did not exist 50 years ago. They will, if we continue to invest in them, be significantly more capable 50 years from now. The story of planetary defense is not a story of a threat that we cannot address. It is a story of a threat that we are in the process of learning to address, which is a different and considerably more hopeful story. Let that be the last thought of tonight. Not the impact and not the crater and not the millions of casualties of the hypothetical impact we imagined, but the spacecraft already en route, the telescopes already running, the orbits already calculated, the knowledge already accumulating in the databases of the Minor Planet Center and the NASA Center for Near-Earth Object Studies and the European Space Agency's NEO Coordination Center and dozens of other institutions whose staff show up every day to do the work of knowing where things are and where they're going. Let that be what you carry into sleep. The watch is kept. The sky is known. The serpent has a number and a name and an orbit precise to within a few kilometers, and will pass us by in April 2029 as safely and as magnificently as the math says it will. Outside your window, the stars are moving in their ancient circles, the same stars that the Egyptians watched from the banks of the Nile, the same stars that the first humans looked up at before they had any words for what they were seeing. They are indifferent to whether you sleep or wake. The universe does not arrange itself around your schedule, but somewhere up there, specific, known, tracked, is the rock that was named for the Serpent of Chaos, carrying its 1-200 megatons quietly through the dark, 3 years from its closest pass of this small blue world. It will miss. The math says so. 3 spacecraft will be there to watch. 2 billion people will look up. And somewhere in that watching, that ancient, essential, irreplaceable human act of looking up and paying attention to what moves through the darkness, is the answer to what the ancient Egyptians were doing in their temples with their wax figures and their spells. They were keeping attention alive. They were refusing to let the vigilance lapse for even a single night. They did not have radar or orbital mechanics or spacecraft. They had the instinct that those things would eventually be built from, the deep human conviction that the darkness deserves to be watched, and that the watching matters, and that the sun, if we are paying attention, will come up in the morning. It will come up in the morning. Sleep now. The sky is watched. The orbits are known. The serpent passes by. If you made it this far, you know there is more where this came from. Every week, another story. Another journey into the deep history and the far edges of the world and the universe we inhabit. Subscribe, and I will see you in the next one. Good night. There is one final thing worth understanding about Apophis before we let it go, before we let the name drift back into mythology where it came from and let the rock itself continue its silent orbit through the inner solar system. It is not unique. That sounds like it should be alarming, and in a practical sense it is, because Apophis's uniqueness as a public concern comes partly from its discovery at a moment when our instruments were good enough to find it and calculate its trajectory with enough precision to generate a credible threat probability. There are, according to current estimates, roughly 25,000 near-Earth asteroids larger than 140 meters, of which approximately 40% have been catalogued. The remaining 60% are unknown to us. They are out there in the inner solar system, crossing and recrossing Earth's orbital path on timescales of years to decades, invisible to the survey telescopes that have not yet swept the patch of sky where they currently sit, waiting to be found by the next generation of instruments. Most of them are safe. The vast majority of near-Earth objects, when their orbits are fully calculated, turn out to pose no threat to Earth in the coming centuries. The solar system is enormous, and the Earth is a small target, and the geometry of near-Earth asteroid orbits, while it brings them close enough to us to be classified as potentially hazardous objects, does not mean they are on collision courses. Finding them and calculating their orbits is the work of distinguishing the few that might pose a genuine threat from the many that are simply neighbours in the solar system, rocks that share the same general neighbourhood as our planet without presenting any danger. But the work matters. Every asteroid found is one whose threat status can be definitively established. Every orbit calculated is one fewer unknown in the equation of how safe the coming centuries are likely to be. And every instrument built to find them faster and more completely, every survey telescope brought online, and every radar dish pointed at a passing asteroid, reduces the population of unknowns and expands the catalogue of the known. The Vera Rubin Observatory, now operational and scanning the southern sky in unprecedented detail, is expected to find roughly 100,000 new solar system objects within its first year of full operations. Among those 100,000 new discoveries will be near-Earth asteroids, and among those near-Earth asteroids will almost certainly be objects whose orbits require careful analysis before their threat status can be established. Some of them will briefly touch the lower levels of the Torino scale before additional observations clear them. A few may occupy the attention of the planetary defense community for years before their orbits are refined to the point of certainty. None of them will be quite what Apophis was. Apophis was the first. It was the proof of concept, the demonstration that the survey systems built in the 1990s and 2000s were capable of finding the rocks that needed to be found with enough time to respond. It earned its name honestly. It was for 17 years the most famous potentially hazardous object in history, and it will remain the most studied asteroid of its size when the missions of 2029 have finished their work. The Lord of Chaos, the serpent from the darkness, the thing the ancient Egyptians burned their wax figures to protect against. It came and it passed, and it taught us what we needed to know. That is perhaps the best possible outcome for a rock with a name like that.